I've got up on the board here the derivative formulas for all 6 of the inverse trig functions. Now, we've just derived these 4. Here's what you're responsible for. The 4 that we derived together, you should know those formulas. I could just ask you, what's the derivative of arccosine in the context of some problem, and expect you to be able to tell me that in 15 seconds. You should just know that. I could also ask you to derive them. Now, you're responsible for being able to derive any of the 6, the 4 that we did together or these 2 as well. I'm not going to hold you responsible for having these 2 memorized, although it's very easy to, because it turns out that the derivative of arccotangent is just the opposite of the derivative of arctangent. And the derivative of arccosecant is just the opposite of the derivative of arcsecant. So easy to have them memorized, but these are the 4 that we work with the most. So I expect you to know those formulas, but I expect you to be able to derive any of the 6 of them. You will, in the check-in assessments, talk a little bit about how to restrict the domain of cotangent and cosecant in order to get an invertible function, and therefore define what the range of the inverse functions will be. Okay. All right, I also wanted to show you one other thing. In the last problem, we had x equals secant y, and we had that y was in the interval from 0 to pi over 2, union pi to 3 pi over 2. And we needed to figure out what tangent of y was. And the way we did that was to use our Pythagorean identity. I think that's the simplest choice in this case, so that's what I did in all of the functions where we had to solve for a trig function. Okay. Just want to show you that there's another option, and that's called the triangle method. If x is secant of y, I can say, oh, so y is my angle, and x is secant. And I know that secant is the reciprocal of cosine. Okay. So cosine would be adjacent over hypotenuse. So secant would be hypotenuse over adjacent. Oops, sorry, just x over 1. My bad. No absolute value yet. Notice x is the same as x over 1. So I can go ahead and do this. Okay. Then I could use Pythagoras to solve for this side. I know that 1 squared plus, I'll just call this p for opposite, plus p squared should be x squared. So p squared would be x squared minus 1. And p would be the square root of x squared minus 1. And I'm choosing the positive root here because it's the side length in a right triangle. Okay. So we get this, root x squared minus 1. And then I can say tangent of y is just opposite over adjacent. So that's root x squared minus 1 over 1. And that's root x squared minus 1. Very nice. Okay. I like that method, but we're only halfway done because this picture goes with this interval. I have assumed by putting y as an angle in my triangle here, I have assumed that y is an acute angle. And I took the positive root here because I was assuming that everything was positive. Well, side lengths of triangles for acute angles, which would put me in quadrant 1, are positive. But in quadrant 3, not everything is positive. So, if I want to use the triangle method, and it's a perfectly legitimate method, I have to draw 2 pictures, one for each quadrant. So I would also have to draw this, where I said, there's my angle y, and then I've got a reference angle alpha, because there's no angle in quadrant 3 that's going to fit into a right triangle. Okay. Then what I can do is I can say if x was secant of y, secant of alpha is going to be the absolute value of x. That's super important because if I'm in quadrant 3, I know that x is actually representing a negative number because x is secant of y and secant is negative in quadrant 3. Okay. So, but the reference angle always gives me the correct absolute value for my trig functions. I would just, if I'm taking secant of y, attach a negative sign to that absolute value. So I can say secant of alpha is the absolute value of x, which is the absolute value of x over 1. And then I can label my sides, absolute value of x and 1. Now that's actually really important because x itself is negative. The way I get secant being a negative number is that this 1, if I were labeling signed sides of my triangle, and I'm not, I'm actually labeling this for alpha, but if I labeled it for y, I could label signed sides, but the hypotenuse is never negative. What makes things negative is the fact that this would be a negative 1 because we're moving to the left. Okay. So then I could solve again for the opposite side, and that would become the square root of x squared minus 1 using the same just Pythagorean theorem. Okay. And so then I could calculate the tangent. And I would say tangent of y, it's going to be a two-step process. We're in quadrant 3, so it's going to be positive. And then I'm going to just attach tangent of alpha here, which would be root x squared minus 1 over 1. So I get the same formula that I got in quadrant 1. But this picture only proved it half of the time. If I want to prove it all of the time, I need a second picture for my angle in quadrant 3. And that's particularly important with secant and arcsecant, because if we were in quadrant 2, we would not get the same formula. We would get different formulas. So I have no problem with you figuring out, if you know that x is secant y, with you figuring out what tangent of y is by drawing triangles, plural. But you gotta draw two. And the same holds for any of these. If you are working in two quadrants, drawing one picture where your angle is acute doesn't prove anything for the second quadrant. So even though with arcsine and arccosine, we're going to get the same formula in both quadrants as well, if you're using the triangle method to prove that, I want to see two pictures, one triangle in each quadrant. For that reason, I recommend going with just using identities, because then we were able to sort of do it all at once. We were able to say, hey, my angle y is in one of these two quadrants, but in both of those quadrants, my trig function is positive, so I'm going to choose the positive square root.